we're going to cover the second half of section 6.6 today. Section 6.6 is exponential and logarithmic equations. We've done exponential equations, so now it's time for logarithmic equations. So get to this document camera up. When we talk about logarithmic equations, we mean equations of this form. We've got a logarithm equal to a number. And solving equations of this form is actually relatively straightforward. There are two ways we can think about a problem like this. Let's illustrate these ways with examples. So we won't try to do this in generality. We'll look at an example, say the logarithm base 5 of x. And I'm going to need my calculator, so there's going to be a brief pause here while I find it and get it up on my screen. There it is, ready to share when necessary. So the first way you could approach a problem like this, and I would argue the easier way, although it's not what most textbooks do, comes straight from the definition. Remember that every statement about a logarithm is a statement about an exponential function and vice versa. So this is an equation we're trying to solve. I mean, the logarithm base 5 of x, let me get my screen up. The logarithm base 5 of x is a function, and we are trying to figure out where it equals 7. Sorry, this stuff is kind of in the way. This inset is, let me move it a little. So we're trying to find when this function equals this horizontal line. It's an equation. But if we rewrite it, it stops becoming an equation and just becomes an explicit statement about what x is equal to. X is equal to 5 to the 7th, when we take this logarithmic statement and write down the equivalent exponential statement. And 5 to the 7th, we can just quickly calculate. X equals 78,125. So that's a way of solving logarithmic equations. And I've come to think that this is the simplest and most straightforward way. There's another way we could think of solving a problem like this. It used to be the way I preferred and taught my students. I've kind of, as I say, had a change of heart in recent years. Now I tend to think that just rewriting the logarithm is the way to go. But there's another way we could approach this, and that's that if you have an equation, you can do the same thing to both sides of the equation. That's a concept you're certainly used to by now. It's the basis of algebra. So in particular, we can take both sides of the equation and put them both into an exponent. Why this exponent in particular? Why 2 instead of 3 or 4 or anything else? Well, we used the same base as the logarithm. And that causes the left-hand side to cancel. X equals 2 to the 4th, 2, 4, 8, 16. And going back to what I have written up here, we could go directly from here to the statement that 2 to the 4th equals x. So it's kind of all one here, whether you want to think of solving these equations as just rewriting statements about logarithms, as statements about exponentials, or if you prefer to think of it a little more algebraically, as manipulating both sides of an equality, you wind up at the same place in either event. Let's look at a few more examples of this. We'll complicate things a little. For our first kind of level of complication, we are looking at equations like this. The logarithm base a of x equals b. And we can solve such equations, whether we want to think of it as algebraically manipulating both sides of this equation, or whether we prefer to think of it simply as rewriting a statement about logarithms as a statement about exponentials. We can get x out of this thing. For that to work, though, we need to have nothing else on the side of the equality that has the logarithm on it. So there should be no addition over here. There should be no multiplication. And so on. Just a logarithm by itself is what we're aiming for. So if you have something like 3 times the natural log of x equals 7, you're going to have to do some manipulation, because this multiplication we have here has to go. So our first step has to be to get rid of that multiplication. And multiplication is gotten rid of via division. We were multiplying by 3, so we divide both sides by 3. And now we have something that we can work with. Let's solve it just by rewriting the logarithm. To do that, remember that the natural logarithm is the logarithm base e. So this is rewritten as e to the 7/3 equals x. Go to our calculator. E appears twice in our calculator. It appears over here, and you could type in e to the 7/3. There's also an e to the x command over here. It hardly matters which you use. It's a matter of a single button press. equals 10.31258. Let's do another example where it's a logarithmic equation, but we have a few complications to deal with. Maybe we have addition. 7 plus 3 times the common logarithm of x equals 12. And we can solve this by rewriting it. But to do that, we need the logarithm by itself. We don't want this addition, and we don't want this multiplication. So we need to eliminate these. Undoing the order of operations, first we'll get rid of that 7. Via subtraction. Addition is undone via subtraction. And now we have multiplication. And multiplication is undone via division. So this is the common logarithm. For purposes of rewriting this, remember that the common logarithm is the logarithm base 10. So remembering how to rewrite the statement about a logarithm as a statement about an exponential, 10 raised to the 5/3 equals x. 10 to the 5/3 equals x. And as for what 10 to the 5/3 is, 10 to the power of 5 divided by 3, 46.41588. And that's just sort of at the bottom range of what we can see in the document camera. So it's about time to start a new page, I reckon.